And welcome to High School Physics Explained, and today is the first in my series, How Well Do You Know? And today I'm going to do a video on how well do you know projectile motion. And I'm going to go through a series of multiple choice type questions and then give you an explanation of how the answers are derived. So the best way to use these videos is to actually pause the video after each question and try it yourself, and then I will go through the answers. So let's start with the first one, a fairly simple one. Here we have a diagram that shows the path of a cannonball fired from a cannon, and you're supposed to identify which set of vectors represents the horizontal and vertical components of the cannonball's velocity. So let's have a look at the answers. Well, the important thing about projectile motion is to understand that projectile motion really is two motions at the same time. We have a vertical motion, and that is under the influence of a gravitational field. Namely, in this case, that will result in an acceleration in this direction. You'll also have a horizontal motion, and that is not under the influence of a gravitational field, and therefore, in ideal circumstances where air resistance is ignored, you have constant velocity. So if we remember that and look at the questions, here in a projectile motion, the cannonball is traveling at a constant velocity from left to right, and it is accelerating in the vertical. Initially, it will cause this to be slowing down as it goes up and then speeding up as it goes down again. With that knowledge in mind, then the only possible answer is C. This second question is similar to the previous question. And here you've got three places, X, Y, and Z, and you are supposed to work out what are the vectors for the velocity and the acceleration. So again, the important thing to remember here is that this object is moving in a projectile motion. It has horizontal and vertical components. Generally though, the actual trajectory is actually the direction of the velocity at any given instant. So the velocity is going in that direction. It's a combination of the horizontal and vertical. At the top of the trajectory, it's going horizontal. There's no vertical velocity whatsoever. And of course, at Z, we have both vertical downward velocity and horizontal velocity. The important thing here, of course, is that the horizontal components are constant, and of course, the vertical components are changing. And so that means the velocity clearly is going up, across, and down, and so that actually looks at B, C, and D. The most important thing about projectile motion is that the acceleration is constant throughout the whole path, and therefore the only possible answer is C, because all these vectors show the acceleration to be down at all times. So the next question is more about understanding the perceptions of projectile motion. So here we have a trace of a ball following a projectile path, or a parabolic path, and it asks which of the following statements is true. Is the velocity always changing? Is the acceleration of the ball keeps changing? Is the velocity of the ball at the top of its motion 0? And is the acceleration of the ball at the top of the motion 0? Well, this one is fairly easy now that I've used the previous two questions to explain some features of the projectile motion. And the only possible answer here is A. The velocity is constantly changing. Although the horizontal velocity is constant, the vertical velocity is changing due to the acceleration, due to gravity. And so therefore the combined velocities are always changing. Let's go through also why B, C, and D are incorrect. And one of the good things to do as you go through multiple choice questions is to ask yourself, what are the reasons why the other alternatives are incorrect? It's a good way of really reassuring yourself and to show that you have an understanding of the concepts involved. In part B, it says the acceleration of the ball keeps changing. Well, we've established that the acceleration is constant, so therefore that cannot be correct. C says the velocity of the ball at the top of its motion is 0. Well, actually the velocity isn't 0. It's still moving horizontally. The vertical component is 0, but the whole overall velocity is not. And finally, D says the acceleration of the ball at the top of its motion is 0. And again, the acceleration is constant. It doesn't change. So therefore, that discounts D as well. So now we have a pictorial version of projectile motion. The dots show the position of the projectile at equal time intervals. And you have to work out which is the best path. I'll give you a few moments to work out the answer. Now this question, although in some ways is similar to previous questions, we are actually now seeing a diagrammatic view. And generally, that is a higher order type of question. You're actually interpreting not statements, but interpreting diagrams in this case. And so you have to look much more closely. So let's have a look at the particular situation, remembering that we have equal spacings is equal amount of times. So what we're looking for is that the spacings horizontally between each of the dots is constant, because the displacement is constant horizontally, the velocity is constant horizontally, therefore the time taking place between each dot is constant. With that in mind, it's pretty clear to see the number of answers don't fit the bill. This one doesn't fit the bill because we've got 2 blocks here, but here we've got only 1. So C is ruled out automatically. If we look over here, you can see there's 1 dot difference here and 2 dots difference here. So therefore, again, horizontally, it's supposed to be constant. That rules that particular situation out. Now, A and D are left over. Now, again, we need to see changes in the time because of the fact that the velocity is changing, and so therefore the time intervals are also changing. So if we look very carefully, what you're expecting to see is clearly a change. So we've got 1 dot, 1 dot, 1 dot, now 2 dots, and now 2 dots, and now 2 dots. So really what's happening here is that we have a constant velocity. You can tell that because the actual slope of that line is straight. So in other words, we have a constant velocity in this direction. Well, that is actually not true to projectile motion, so that automatically rules A out. Now let's have a look at D. We have constant distances between the horizontal components, and then what we have here is a 1. Here it's the same, but the odd chance is that if we were to track the ball would actually rise at this point over here. And then we have 1, and then we have 1.5, and then we have clearly 2 or 3, and therefore, in this case, this is the projectile motion situation, so D is the answer. Here's another question, and in this case is the classic question of 2 objects fired at the same height, and what is going to happen in terms of them landing. And so we've got 2 balls fired simultaneously from the same height, and the results are shown, and asks which statement is correct in terms of what happens. Is it that X hits the ground before Y because it's closer? Is it Y that hits the ground before X because it has the higher velocity? Do X and Y hit the ground simultaneously with the same velocity? And do X and Y hit the ground simultaneously with different velocities? I'll give you a moment to answer. Well, the important thing is that with projectile motion, the 2 motions involved in any object undergoing projectile motion, of course, is what's happening vertically and what's happening horizontally. And one of the Galileo's analysis of projectile motion is that these 2 motions are independent of each other. They do not affect the other. And so therefore, the fact that this ball drops the same height as this ball, they will take the same amount of time to reach the ground. It's regardless of what's happening horizontally. Because of that, A and B are automatically excluded. C and D both said they hit the ground simultaneously, and that is correct. But what's important to understand is that the velocity at which they strike is a combination of what's happening vertically and horizontally. So although they arrive with the same vertical velocity because they are dropped from the same height, they clearly have different horizontal velocities because Y travels further. So the combined velocities for X and Y will be different because of the fact that their horizontal components are different. So the only answer possible is D. Again, this is a higher order question because you're now interpreting graphical information in this case. So a ball or a stone is thrown upwards from the top of a cliff at an angle of 45 degrees to the horizontal. Which graph of the vertical component of the stone's velocity as a function of time best describes its motion? I'll give you a moment to think about it. The important thing is with questions like this is not to get too bamboozled with graphs. It's again important to understand what's happening with projectile motion and understanding basically what graphical information of motion can tell you. And the first thing is to remember that when we have a velocity time graph, that is what is happening here, the slope of the line will always give you the acceleration. And so regardless of the fact that this is a component velocity or whatever, The important thing is about projectile motion, the only acceleration that exists for a situation here, regardless of the angle thrown, is that the acceleration is constant. With that in mind, that automatically excludes A, B, and C. Only D has actually the acceleration being constant. Now, it is a negative value, but that's no problem at all because we are assuming that the initial velocity is thrown up, is in a positive direction, and therefore the acceleration causing the ball to slow down must be negative initially. This point here represents the point at the top of the trajectory of the ball, and then of course it returns back to zero. It's now traveling in the same direction as the acceleration, so you expect it to be negative. So D is our answer. We're getting a little bit more difficult now as we go along with these questions. Here a projectile follows a parabolic arc from point A to point B and ends as sketched in the diagram, and the displacement of the projectile is measured from the launch position. If air resistance is neglected, which statement is correct? Is it A, that the total time is twice the time to reach the maximum height? Is it B, the velocity has a maximum magnitude when the displacement is zero? Is it C, the vertical component of the acceleration depends on the direction of the initial velocity? Is it D, the horizontal component of the final displacement depends on the initial velocity? I'll give you a moment to think about which is the best answer, and also to give yourself a little bit of time to think about why the other answers will be incorrect. So now let's go and look at it. Now clearly we have an object undergoing projectile motion, and if we were to stop at a point over here, you can see there's a symmetry over here. So therefore, being that symmetry at this point junction here, the time it takes to go up here is the same it takes the time to go down in this section over here, assuming it's here. Because of the symmetry and because of the parabola, the velocity that is fired in this direction, or at least the magnitude of that velocity at which it's fired here, is actually the same value of the velocity over here when it actually reaches this point over here. Now that, of course, is the magnitude. It's traveling in a different direction. Interestingly enough, though, the angle that it is launched here will be the same angle here. Of course, up here, the velocity vertically is zero, but it's still moving horizontally, and of course that is constant throughout the whole journey. See what I've done? I've actually interpreted the graph a little bit more before I even look at the possible answers. Since I know that this ball continues further on, that the velocity when it gets to B is going to definitely be greater, because here it already has the velocity that it had initially, and so it is now continuing to fall, so I expected the velocity to increase. So let's have a look at the responses. It says the total time of flight is twice the time to reach the maximum height. Well, that's incorrect because the time up here is the time down here, but of course it's going to continue further on. And so therefore the total time is not twice this. There's clearly a different two times. A can be excluded. Part B says the velocity has a maximum magnitude when the displacement is zero. Well, when is the displacement zero? Well, it's the displacement from A. So the horizontal displacement is along here. The vertical displacement is here. But at no point is the ball at a zero displacement, except of course when it's launched. But the velocity is not a maximum at this value because we've already established that it speeds up and continues on from V down to here. So therefore B is incorrect as well. C, the vertical component of the acceleration depends on the direction. Now this statement here clearly is incorrect because it says somehow that the acceleration is variable depending on the direction of the initial velocity. We've stated time and time again that the acceleration is constant throughout the whole journey. So C is also incorrect. Finally, it says the horizontal component of the final displacement depends on the initial velocity. And that is of course true, because the horizontal displacement is always equal to the velocity in the horizontal direction multiplied by the time of flight. So in that case, because it's constant, you can see we have just a simple average velocity formula over here. Clearly the final displacement does depend on the initial velocity. So D is correct. Now, this is getting a little bit more difficult. We've got a batsman here hitting a ball, and it has two dots here that represent basically the same maximum height above the ground. But Q, of course, travels further. And the question is, which of the following is different for balls P and Q? Is it the time of flight? Is it the initial velocity? Is it the gravitational force? And is it the gravitational acceleration? Well, let's first of all rule out two obvious incorrect ones. I've said time and time again the acceleration is constant no matter what. Therefore, since these balls are identical in mass, we can therefore say the gravitational force on these balls is exactly the same. Therefore, also the gravitational acceleration of these balls is exactly the same. The answer is not that they're different, so therefore C and D are automatically excluded. But what about the time of flight and the initial velocity? Well, let's have a look at knowing how we solve this question. We have, of course, the way to solve any question involving projectile motion is to write down all your variables like this. And you always have 5 variables. And I'm going to look at it from 2 different perspectives. I'm looking at it from P and Q. Now, we're already told that they travel the same height. So therefore, the R of P is equal to the R of Q. That's exactly the same. We've established that both balls are going to have exactly the same acceleration. And finally, they both reach maximum height here at this point over here. So they both actually have a final velocity at these 2 points of 0. As you can see, we now have 3 variables that are exactly the same. That means their vertical initial velocity is going to also be exactly the same, and their time to reach the time is also exactly the same. Then you say, hold on, clearly both are there. But remember, the initial velocity of the batsman hitting the ball is not just the vertical, but also the horizontal. So even though the vertical velocities initially are exactly the same, it's clearly that the fact that P and Q travel further distances, that their horizontal velocities are different. So combined, their initial velocities are different, giving B the answer, and A, of course, is incorrect. Let's have a look at the next question. And in this case, we have a mathematical question. It says a projectile was launched from the ground and it has a range of 70 meters and was in the air for 3.5 seconds. At what angle to the horizontal was it launched? Pause now and try to work it out, and then I'll go through the answers. Of course, that to solve these questions best is to break up your question into two components, the vertical and the horizontal components. And that's really important to solve this. And automatically you write down all the 5 variables that you have for the vertical. I could do that for the horizontal, of course, but acceleration doesn't exist, so therefore V and U are exactly the same. So I end up writing just simply V, R, and T. And to be absolutely clear, we're dealing here in the vertical components over here, and over here we're dealing with the horizontal parts over here. We then substitute everything in that we know. And so the vertical velocity over here, we don't know, but we need to know it. So I'm just going to leave this as Vx. My horizontal displacement is already given, and that's 70, and my time is equal to 3.5. In the vertical, the velocity that it actually lands at is the same velocity that it leaves at because of the symmetry of the projectile motion. And so what I'm going to write here is I'm going to make this Vy, and I'm going to also make this Vy, but because it's in the opposite direction, it's going to be negative. My acceleration, of course, is negative 9.8. Of course, I should put all the units in. I haven't done that over here, but there we go, we'll do that. And the vertical displacement from beginning to end is 0, and the time is still 3.5 seconds. Now, with that in mind, we now can solve it mathematically. So if we work out the horizontal velocity and we work out the vertical velocity, we can combine those two to work out the angle, because the horizontal velocity is going to be Vx. The vertical initial velocity is going to be Vy, and you can see by using simple trigonometry, we can actually work out the angle. So let's have a look at the equations in both the vertical and the horizontal. If I clean this up, you can see that the vertical velocity Vx is equal simply displacement over time. That gives me 70 divided by 3.5, and that is equal to 20 meters per second. So hey presto, we've already got the horizontal component. Now, if we look at the vertical, the best way to do it is using r is equal to ut plus a half at squared. And if I'm substituting everything in, you can see I get 0 is equal to u. Now, remember, we're looking for this, so this is going to be equal to our Vy multiplied by 3.5 plus a half by a. Now, a is negative 9.8, so I can work that out. Negative 4.9, like so, multiplied by 3.5 squared. If I rearrange that, you can see that I will get negative Vy by 3.5 is equal to negative 4.9 by 3.5 squared. Now, of course, the negatives cancel out and the 3.5 cancel out. So I end up getting a Vy is equal to negative 4.9 multiplied by 3.5. Well, that's going to give me an answer of 17.15. So now I can say, I can fill this in. I've got 17.15 for the vertical. I already have 20 for this. And if I use the inverse tan, I'm going to get approximately 40.6 degrees. And so the answer here is B. Now, some of you may be saying, hold on, that's 40.6, but the answer is 40. And the thing to remember here is that this value here of 3.5 isn't necessarily precisely 3.5. It's 3.5 to two significant figures. And so therefore, the actual time here for exactly 40 will be slightly different, but into two significant figures, we're going to get 3.5. Next question. Napoleon attacked Moscow in 1812 with his cannon firing a shot at an elevation angle of 40 degrees. Napoleon then decided to fire a second shot at the same speed but an elevation angle of 50 degrees. Which of the following observations would Napoleon expect to be true about the second shot when compared to the first? Is it the longer range, shorter range, longer time of flight, shorter time of flight? Well, the key to this question is to understand that we have two angles here that they're fired and that they are clearly complementary. That is, they add up to 90 degrees. What that means is that for any angle less than 45 degrees, which is the angle for maximum range for any given velocity, that if the two angles are complementary, that is, they add to 90, they give you exactly the same range. Now, I've already produced a video explaining how that is worked out, and I encourage you to have a look at that if you're not sure why that is the case. But because of that fact, therefore, A and B are both excluded because they actually have the same range. However, although they have the same range, the fact is that if it's fired at a higher angle, it's under the influence of gravity for a longer time, so it actually has a longer time of flight. And so therefore, the question says, which is true about the second? So that's the 50 degrees. Well, it clearly has a longer time of flight, and D therefore is also ruled out. For my final question, the most challenging of all the projectile motion questions in this video, we have another question involving some calculations, and I'll give you a moment to work this out. A ball is launched horizontally from a cliff with an angle of velocity u meters per second. After 2 seconds, the ball's velocity is in the direction of 45 degrees from the horizontal. What is the magnitude of the velocity in meters per second at 2 seconds? Pause. Okay, so in order to interpret this question, it is really worthwhile to draw a diagram of the velocity or the motion of the ball after 2 seconds. So we know that we have a cliff, of course, and it is fired over here like under projectile motion. And then at a certain point, 2 seconds, it actually now has, as we've told, is now traveling in a direction of 45 degrees. So in other words, the velocity in this direction is 45 degrees. Well, that means it's having a horizontal velocity in that direction and a vertical velocity in that direction. And because this is 45 degrees, the horizontal component of its velocity is now equal to the vertical component of this velocity. So let's enlarge that a little. Well, The first thing is to know that the initial velocity is u. That doesn't change along the trajectory, so we automatically know that this is u. So we're already at the step of understanding how we can solve this particular vector here, which is what we're looking for after 2 seconds. But what is happening in this direction? Well, the important thing is that we need to go v, u, a, r, and t. We're asked here the vertical velocities. That's the one we're interested in right here. So we'll just call this basically v for the moment. The initial velocity, of course, is 0. The acceleration, of course, is negative 9.8 meters per second squared. And the displacement we don't know, but we do know this is 2 seconds later, so therefore we can put 2 over here. And so then we can say v is equal to u plus at, and therefore our velocity is simply equal to negative 9.8 multiplied by 2, which is equal to negative 19.6. So this is negative 19.6. But hold on, this value here is this value. So therefore, this is also 19.6. Now I'm just going to remove this negative because that only negative is suggesting that it's going down over here. And so now we're in a position to work out this value. And it's clear that the velocity that we are interested in is equal to the square root of 19.6 squared plus 19.6 squared using Pythagoras. And that gives us a total of 27.7 meters per second. D is our answer. So I hope that's helpful. I'll be producing videos like this once a week. My aim is to reproduce them every Thursday, as well as my other explanation videos on every Monday. Thanks for watching. Bye for now.